So, hello everyone, this is Namish, and today we are going to dive into one of the most elegant, powerful, and absolutely unbreakable laws in mathematics, that is our Cauchy-Schwarz inequality. Now, before you think this is just another, or you can say a dry formula, so let me stop you right there. This single inequality is a structural pillar of our universe. Without it, quantum mechanics collapses. In fact, if you want to understand the terrifying mathematics of a black hole, you need Cauchy-Schwarz, right? Like at the edge of a black hole, the event horizon particle fluoresce into existence and fall in, creating what we call Hawking radiation. The absolute limit of all these quantum fluctuations are bound by Heisenberg's uncertainty principle. And guess how? The uncertainty principle is mathematically proven. Yeah, you guessed it right. That's Cauchy-Schwarz inequality. So, basic this inequality acts as the ultimate cosmic guardrail that ensures physics doesn't tear itself apart. So if you find this journey into the heart of math and it's if helpful, so please smash that like button and share it with your friends. Okay, now let's unlock the secret together. Okay, imagine we have two separate collections of real number. We call them set A and set B. So set A contains n elements, which absolutely are all real numbers, and set B also contains n real numbers. So what Cauchy and Schwarz discovered is a beautiful relationship between how these numbers interact. If you pair them and multiply them together, like a1 b1, then a2 b2, then a3 b3, and so on till an bn, and add up all those products and then square the whole thing, the final number, what we got, it should be always less than or equal to what you get if you square all the elements of set A and square and add them up, and then you have to do a product with uh, squares of a set B and add all those numbers. So if you want to generalize this whole thing, you can write this as your uh, summation of AIBI. That is what the product of set A element and set B elements, and then you have to add them all those things, and then you have to square the whole thing. It should be always less than the product of two individual things. That is the sum of squares of A elements and the summation of square of all B elements. So now we are going to see its proof. So to prove, we need to define our sandbox function fx, right? Let me show you. Okay, so it is visible now. So we have to define our function as a sum of perfect squares of a linear function. Right. So like here we have assumed our function fx as is sum of squares of linear functions for all x belonging to real numbers. So here we have considered our first linear expression as a1x minus b1, and then we have to square similar linear functions uh, as here I have to write a2x minus b2, and then we have to square similar terms, similar things. Then here at the last we got a n x minus b n whole square. So this is our assumed function, and now we have to do some sort of things and very fundamental things. Okay, so before proceeding, let me tell you that because you can see that every single term is square, so no term can be negative. Even if I can say a1x minus b1 is a negative number, then the square of this thing should always be positive. Or there is other chance that it might be zero, but as you can see that the whole function will never be negative. So I can simply say that the our assumed function will always be greater or equal to zero, right? So let's expand each bracket. So as we got fx as squaring the first bracket, so we will get a1 x a1 square x square, then plus b1 square, then minus 2 a1x b1, and similarly you have to open all these brackets. So we will get a2 square x square plus b2 square and minus 2 a2x and b2, and similarly you have to do till the last bracket. So finally we will get an square x square plus bn square minus 2an bn x, right? I hope so it is visible to you. Now what we have to do is just club all the similar terms, like we have to club all the terms which contains x square, then x, and then all the constant part as well. So I can write this as fx as, if I take x square common, then we will get what, a1 square, then a2 square, and so on till an square. So we will get a1 square plus a2 square plus and so on till n square, and basically this is coefficient of x square, and then we will get minus 2, and a1 b1 plus a2 b2, and so on till an dn, and this is what coefficient of what x, and then we will having constants part as b1 square plus b2 square till bn square, right? So this is our function after expanding all those brackets, right? Or I can say, yeah, I can simply represent it as in form of fx is equal to a, here capital A is basically what it is representing sum of all a is square, like capital A is here what, a1 square plus a2 square plus a3 square, and so till n square. So this is a, so I can write this as a ax square, and let's assume the product of a1 b1 and the sum of all those things plus a2 b2 plus a3 b3 till n bn as b. So I can write this as minus 2 bx, and let's say our constant part as c. So as we already saw that the our function, our assumed function is always greater or equal to 0. So I can say that this whole thing will be greater or equal to 0. Let me write what we have called a. So a is here what, summation of ai square. Here I is varying from 1 to n, and so on. B as summation of ai and bi, and c is what, summation of bi square. And okay, so we are on the next page, and this is what we got earlier. Because our fx is always greater than or equal to 0, so its graph is basically a parabola which will facing upwards, which will face upwards, and that number goes below the x-axis. It either floats entirely above it or perfectly touches the x-axis at exactly one point. Like this is our Cartesian system. So our parabola must be an upward parabola, and it might be not touching x-axis, or it may touch at one point on the x-axis. So this is our y equal to when the x equal to 0. So for this condition, or as you recall from class 11th mathematics, for a quadratic equation to never cross below the x-axis, its discriminant must be less than or equal to 0. So what I can say, the discriminant of our quadratic function should always be less than or equal to 0, right? So what is discriminant? That is b square minus 4ac. It should be always less than or equal to 2. What we have to do next is just put the value of b, a, and c respectively. Here b is what, coefficient of x, and here a is what, coefficient of x square, and c is constant part, right? So let us put the value of small b, a, and c. So small b is here what, that is minus 2b. So the square of minus 2b, and then minus 4 into A is a capital A and C is capital C. So this whole thing should be less than or equal to 0. So squaring minus 2b square, we will get 4 capital B square minus 4 into capital A into capital C. It should be always less than or equal to 0. So as you can see that uh, you can divide the whole inequality by 4 on both sides. We will get capital B square minus A into C, that is less than or equal to 0. Or I can write it as capital B square is less than or equal to A into C. So here what is B and what is A and what is C? As we have saw this thing earlier, that okay, now let's just substitute our original massive brackets back into B square with B square and A and C. So what we have defined capital B, it is summation of AI and BI, where I is varying from 1 to n, and this is what, this is capital B, right? So we have to square this thing, and this thing is less than or equal to We have to put the value of A and then we have to put the value of C. So A is what? We have defined capital A as a summation of AI square, where I is varying from 1 to n, and we have defined C as summation of square of B. Like here, I is varying from 1 to n, then we do have BI square. So on putting the value of capital B and A and C, we our Cauchy-Schwarz inequality. So this is how Cauchy-Schwarz inequality is beautifully programmed, and it is very simple proof. But before ending the video, anyone may ask when does this inequality becomes a perfect balance? Like when does the left side perfectly equal to the right side? Yeah, as you can see, there is inequality which is less than or equal. So we are very interested to see when this inequality uh, converts into equality. So this is very simple, and we can check this thing from our very basic sandbox function, that is if fx is equal to 0, right? So our sandbox function was what? Our sandbox function was fx as some square of linear functions a1x minus b1 square plus a2x minus b2 square and so on till an x minus bn whole square. So if this function fx is equal to 0, then our equality holds in the given inequality. So there is only one condition when this function can be 0, and it is only possible when all the square terms should be equal to 0. Like a1x minus b1 equal to 0, a2x minus b2 equal to 0, and so on till an x minus bn equal to 0. So if this whole thing holds, then only fx equal to 0, and then only we can say that in Cauchy-Schwarz inequality, equality holds, or we can say that there will be a perfect balance in the inequality. From this, we can say that here x is equal to what? b1 by a1, and from this we can say x equal to b2 by a2, and so on, x equal to bn by an. Condition where the equality holds if and only if the ratios of the elements are completely proportional, like a1 by b1 equal to a2 by b2 equal to a3 by b3, and so on till an by bn. So it is something like that if the vectors or sets are perfectly aligned in the exact same mathematical direction, the inequality drops its shield and both sides becomes perfectly equal. So this isn't just a formula to memorize for an example. This is the geometry that holds quantum mechanics together and maps out the boundaries of cosmic anomalies like black holes and so all things. So thank you so much for watching. If you have another creative way to prove this, perhaps using vector dot products or mathematical induction, drop your thoughts in the comment below. I will definitely love to see how your beautiful mind tackle this problem. So don't forget to like, share, and subscribe for more intuitive math journey. See you in the next video. Thanks.